Hello students, welcome. In this video we will discuss chapter 5, which is detection of radar signals in noise and radar receivers. The contents of this chapter are introduction about detection of the signals in noise, matched filter receiver, response characteristics and derivation, correlation function and cross correlation receiver, efficiency of non-matched filters, matched filter with non-white noise, noise figure and noise temperature, displays and its types, duplexers, branch type and balanced type, two types of duplexers. Circulators and duplexers are the topics that we cover in this chapter. Now let us start with the first topic, which is introduction. The two basic operations performed by the radar. What are the two parameters? One is detection, another one is tracking. So detection of target in presence of detection of the presence of reflecting objects is the first primary task by the radar. Second one is extraction of information from the received waveform to obtain target data such as position, velocity and perhaps size. So the extracted information will have three components. One is angular elevation angle, azimuth angle and range data. Along with these three, it will have the Doppler frequency shift also, which will give the velocity of the target, and of course depending upon the amount of echo power that is received, we can estimate the size of the target. Above all, the limiting factor of all the radar systems is its noise. Now we have to study the performance of the system in presence of noise. Now the first topic of this chapter is matched filter receiver. In this matched filter receiver, what is matched filter receiver? A network whose frequency response function maximizes the output peak signal to mean noise power ratio is called the matched filter, which maximizes the output signal to noise ratio is called a matched filter. This criteria or its equivalent is used for the design of almost all the radar receivers. A matched filter is designed such that it maximizes the signal to noise power to its peak. The frequency response function of the matched filter is denoted by h of f, expresses the relative amplitude and phase of the output of a network with respect to the input when the input is a pure sinusoid. This is a standard function. H of f is the frequency response of a filter, which gives the amplitude and phase of the output when appropriate input is applied. In this case, the magnitude of h of f of the frequency response function is the receiver amplitude passband characteristics. In radar, h of f is the frequency response function is the receiver amplitude passband characteristics, because this is the first stage of any receiver. So receiver first stage is it's a band pass filter, so its characteristics. If the bandwidth of the receiver passband is wide compared to that occupied by the signal energy, extraneous noise is introduced in the excess bandwidth, which lowers the output of the signal to noise ratio. The receiver bandwidth should match with the matched filter bandwidth. In some cases, the bandwidth of the receiver pass band is wide compared to the signal energy. In such cases, what will happen? Along with the signal, some other unwanted signal will interfere with the input. All the unwanted signals, we call it as noise. So, as the extra noise introduced in the bandwidth, what happens? It lowers the signal to noise ratio of your system. So, a matched filter is essential at the input to avoid unnecessary noise to enter into the system and degrade the performance. If the receiver bandwidth is narrower, say case 2, if the receiver bandwidth is narrower, then the bandwidth occupied by the signal, then the bandwidth occupied by the signal, then noise energy is reduced along with a considerable part of the signal energy. We wanted to reduce the noise. So what we did, we have narrowed the receiver bandwidth. Because we have narrowed the receiver bandwidth, some part of the signal energy will also lost. What is the result? Again, a low signal to noise ratio. So, an optimum bandwidth is required to have a good signal to noise ratio. Receiver bandwidth B should be approximately equal to the reciprocal of the pulse width tau. What is pulse width? In pulse radar, we are transmitting one pulse and we are waiting for the echo to come. Now, the duration of on time of the pulse is tau. It is inversely proportional to the bandwidth. If you reduce the tau, bandwidth will increase. If you increase the tau, bandwidth will reduce. This is obvious. The receiver frequency response function is assumed to apply for the antenna terminals to output of the IF amplifier. Now, narrow banding is most conveniently accomplished in the IF. The receiver frequency response function is assumed to apply for the antenna terminals to the output of the IF amplifier. The bandwidth of RF mixer stages of the normal super heterodyne receiver are usually large. Why? Because it has to receive F1 and local oscillator frequency F2. When it receives both the frequencies, it should have large bandwidth. Its output, of course, is again the difference signal and some signal. When it has to supply two signals, it should have a very large bandwidth. Therefore, the frequency response function of the portion of the receiver included between the antenna terminals to the output of the IF amplifier is taken to be that of the IF amplifier alone. Because if you consider mixer also, it will become very wide, which is not good for a better performance of receiver. Thus, finally, we need to obtain only the frequency response function of the function which maximizes the signal to noise ratio of the output at the output of the IF filter. If the IF amplifier is considered as a filter with gain and its frequency response is properly intersects to us. So, our IF amplifier must not be chosen such that it will have very large bandwidth, or it should not be chosen such that it will have very narrow bandwidth. It should be an optimum one. Now, let us consider A time invariant filter which maximizes the output signal to noise ratio is H of f. H of f is equal to GA into S of f and e power minus j2 pi f t1, where S of f is frequency domain representation of S of t e power minus j2 pi f t dt. This S of f is the Fourier transform of the voltage spectrum. S conjugate of f is the complex conjugate of S of f. This star S star of f is S should be read as conjugate of f, S conjugate. Now, in this equation, we have mentioned T1 in H of f equation, that T1 is fixed value of time at which signal is observed to be maximum signal. GA is constant equal to maximum filter gain, which whatever the highest signal gain that is possible is given to GA. The noise that accompanies the signal assumed to have uniform spectrum because it is a white noise. White noise always is equally distributed throughout the spectrum. So the noise accompanies the signal is assumed to be a uniform spectrum. Now, it need not we should not expect that it should be Gaussian. Okay, so the filter whose frequency response function is given in this equation 1, has been called the north filter or the conjugate filter, or more normally this is called as conjugate filter. Okay, now the matched filter response function is the conjugate of the spectrum of the received waveform, which waveform expect for the phase shift minus e power minus j2 pi f t1. Now, we should understand that a time delay is necessary in the specification of the filter for reason of physical realizability, since there can be no output from the filter until the signal is applied. The matched filter frequency response function also be similarly written in terms of its amplitude as h of f mod h of f e power minus j phi m of f. Then that equation 1 of the matched filter may be rewritten as, because we have defined its amplitude spectrum as h of f. Now that h of f e power minus j phi f m of f is equal to s of f e power f of phi of f minus 2 pi f t1, where t1 is the signal of maximum energy point. Now, in such cases, this h of f equals the s of f. Now, if h of f is equal to s of f, then what about phi m of f? Phi m of f will be equal to minus phi s of f plus 2 pi f t1. It is very easily you can understand by seeing this equation. So the matched filter may also be specified by its impulse response h of t, which is the inverse Fourier transform of the frequency response function. H of t is equal to minus infinity to infinity h of f e power j2 pi f df, which is very familiar. You can easily write it. You might have studied in signals and systems also. The physical impulse response of the output of the filter as a function of time when the input is an impulse delta function, then the equation 1 and equation 4 gives h of t as, you can replace that with s, s conjugate of f e power minus j2 pi f t1 minus t, because there is a difference between these two signals. Now if f conjugate of f is equal to s of minus f, then we can write it as h of t as shown in the equation 6. The impulse response of the matched filter is the image of the received waveform, that is same as the received waveform. Then that can be shown as shown in the figure 1, received waveform and its impulse response. Both are same, but the only difference is it is that is reverse of that uh, first case. So this is about matched filter and its response. I hope you understood the topic. Thank you.